Okay, I think we're ready now. So we're looking at 31, and we're reviewing from several days ago. So it would have been Thursday when I last talked with you. So they give me a graph of f, and I'm expected to identify the graph of f prime. And so I just go looking point by point, but I want to start perhaps using this chart a little bit. So if I look over here, I'm trying to match up the tangent slope of f with the y-coordinates on f prime. For example, I have this little saying that's on your reference sheet. I might find this can be quite helpful. Every value that you see on f prime, every y-coordinate, is going to be a tangent slope of f. So you can start anywhere. We'll just start kind of left to right here for a second. And we'll notice that right here, this graph of f has a tangent slope. So there's a point here on f. That point has a negative y value, but the slope at that point, the rate of change, is positive. The rate of change at that point is positive. That would mean that when I look at f prime, I have to find a corresponding point where the y value on f prime is also positive, because the y values of f prime are the slopes of f. So I look at this exact x coordinate. This looks to be about x equal negative 1.5 or so. It really doesn't matter what the y coordinate is. We don't really care. What we're looking at is the slope at that point. That slope is negative. So I look down at these choices, and you're going to raise your hand now and tell me, are any of these choices invalid? Like, are any of these graphs of f prime for sure wrong? Like they cannot match up with the fact that up here on f, the slope right here is some positive number. Hands up. You can see if one of those is wrong. About half. Let's go Mason.
A and B.
So if I look at A, kind of in about the same place, this is clearly wrong. Like this y value here is a negative y value. That y value is negative. This slope here is positive. It cannot be A. B for the same reason. The y coordinate here is negative, but this slope is positive. This y-coordinate has to be the same as this slope. So A and B don't work. 2 points if you knew for that one. We want to talk about that. Oh, please.
I'm just confused because aren't those slopes still positive on A and B because they're both going that way?
So 2 more for Ella. So the slope right here on A and B, the slope here on A, B, absolutely positive. That slope is positive. This slope over here on B is also positive. But when we're trying to see how the graph of f corresponds to the graph of f prime, we're not looking at slope on f prime. We're looking at slope on f. So we pay attention to this slope right here. And we note that that slope, that tangent slope right there is positive. And then we go looking on f prime to see if we can find y coordinates that are positive. So this y coordinate is negative. This y coordinate is negative. That's a mismatch. The y coordinate here has to match the slope up here. You okay, Ella? Okay. There we go. Next thing. Raise your hand if you can answer this question. This green slope on f is definitely positive. This slope right here, that slope is definitely positive. If I move further along f, I get to a new slope. That slope is clearly positive still, but raise your hand if you can tell me, is the yellow slope more positive or less positive than the green? Raise your hand. Is the yellow slope more positive or less positive than the green? Yellow slope more positive or less positive than the green? Let's go, Cameron.
Less.
So 2 points if you knew that. The yellow slope is clearly less positive than the green slope, but it's still positive. If I move further up the kind of curve here, this red slope is going to be even less positive, but it's still positive. Danica's chart summarizes a bit of what we're talking about. So when you look at the F column in Danica's chart, and you see an I, that's telling you that if you look at the graph of F, and you see the y coordinates of F going up, see these y coordinates here on F, they are definitely increasing. Each y value is greater than the previous. So the y coordinates on F are increasing. That tells you the only way the y coordinates on F can go up is that the rate at which those values are changing is positive. So these y coordinates are changing, they're increasing. For them to increase, their rate of change must be some positive number. That's why each of these slopes is positive. The slope here is positive. The slope of the yellow is positive. The slope of the red is positive. They all have to be positive because F is increasing. So Danica's chart summarizes that. It says, hey, if you see points on F that are increasing, then you're going to see values on F prime that are all positive. If you see points on F that are increasing, you're going to see values on F prime that are all positive values. So back to Ella's question, 2 more for her, because it was a good question. These dots are all wrong. These dots all have negative values. These dots all have negative values. That is a mismatch. Because F is increasing all along here. When F is increasing, all the values of F prime must be positive. That's why this is wrong, because those are not all positive values. And this is also wrong because those are also all not positive values. Questions about anything? Cool. So Danica didn't invent something. She just kind of summarized the pattern in a nice way, very helpful. So, okay, cool. Let's keep going. So these work okay. These y coordinates are all positive values. That's looking pretty good. These y coordinates are positive. Oh, here's a good question. Please raise your hand when you can tell me when does F stop, like about what x coordinate does F stop increasing? Hands up. At approximately what x coordinate does F stop increasing? So 2 points if your hand is raised. Go, Lexi.
Like 0.8, negative 0.8.
So somewhere about there, about negative 0.8 or so. So 2 points for Lexi. So about negative 0.8, we don't really care about the y coordinate. The y values of F stop going up and they start to go down. So if you looked at Danica's chart, you could make a quick comparison and say, okay, got it. All along here, I'll highlight it in blue, say, the values of F are increasing. And when the values of F are increasing, all the corresponding values of F prime have to be positive, because F prime is the rate at which F changes. If F is going up, then the rate of change of F has to be positive. That's why this worked, and this also worked. But about at x equal 0.8, that's when let me get that to work here. Move this out of the way. So at about x equal 0.8, that's when F starts to go down. When F's going down or decreasing, that would mean F prime's values must be negative. So I have a problem right here. These F prime values are not negative. Those F prime values need to be negative because these values of F are decreasing. So this one also is incorrect. So C has to be the right match. Questions? Michael, please.
So given like the F prime, you really can't say anything about the actual specific points of f of x, like using the graphs. So like, for example, if you were to take like, I don't know, see the answer to this question, you couldn't say where any of the points are, you can only describe the slope of the original one.
Oh, outstanding. Everybody look up. 2 more for Michael. Like, you gotta hear what he said. The y coordinates you see here are not telling you anything about the y coordinates you see up here. They tell us nothing, really, about their actual value. These y values only tell us the slopes or rate of change of the values up here. So we could have drawn the graph of f like this. Like, we can shift f up or down as much as you want, changing the y values completely. But as long as we don't change the slopes, this will still be a perfect match. So this is actually a match for an infinite number of different graphs. They all have the same shape, same curvature, but they don't have to have the same y values. So something like that. So this f prime will match an infinite number of different f graphs, as long as they always have the same curvature, because we're measuring the slope, not the actual y values. Well done. Anybody else? Okay, cool. So we found our match there. Let's just highlight one more thing from Danica's chart where we're here. We talked about how along here, the slopes of f are actually, so f itself is increasing along here, but the slopes of f are decreasing. As we check each slope value one after another, we find that the slope values become less and less as we move along this curve, like this. Let's keep going here for a minute. The slope up here at the top, originally, if you remember what that slope will be, ends up, everybody, who remembers what that slope will be at the very top, where the tangent line looks like this, the tangent slope at that point. About half of this. Go, Ann.
0.
So the slope at the very top is 0. 2 points if you knew that. So that slope is 0. So we had a positive slope, and then a slightly less positive slope, then a slightly less positive slope, and then finally a slope of 0. Then we have a negative slope over here. So all along there, the slope is decreasing. Danica's chart summarizes that. Danica's chart says, if you have a graph of f, and that graph has a concave down shape, then you'll notice that the values of f prime, the slopes, have to decrease. You can see it. This slope is positive, but then the next slope is less positive. And the next slope is also less positive. Then we have a slope of 0. And you have a slope that is even less positive. Sorry, it's negative. So we've got slopes that are decreasing all along here, where f is concave down. Questions? Okay, at this moment, the concavity of f switches. So right about here, go to Cash real quick. So Cash, all I need is positive or negative. The slope right here, would you say positive or negative?
Negative.
So that slope is negative, 2 points for Cash. We'll go to Lupita. If I go here, Lupita, what would that slope be there?
0.
So that's 0. So we're going from a slope that's negative to a slope that is 0, 2 for Lupita. Go to Emily. So we've got a slope that's negative and a slope that's 0. This next slope here, Emily, positive, negative, or 0? Positive, 2 more. So along here, the slopes of f are actually increasing. Negative, 0, positive, and then more positive. That's because f has changed to a concave up curvature. So Danica's chart says when f is concave up, you'll see that the slopes of f have to go up in value. They have to increase. Questions? It's actually the definition of concave up. Concave up means the slope is increasing. So, okay. You can also see it here, right in this section where f is concave down. we know several things. Okay, we know when f is concave down, the values of f prime must decrease. And we can see it right here. Here's the correct answer. All these values of f prime are going down when f is concave down. When f switches to concave up, like here, the values of f prime switch from decreasing, and the values of f prime switch to increasing. When f is concave up again. Okay. This last part of the chart is just a copy of this part of the chart, because f double prime is simply the slope of f prime. So once you're good at understanding how f relates to f prime, you don't have to learn anything new. F double prime relates to f prime in the same way. It's just the slope of f. So that means if f prime is increasing, that means f double prime's values must be positive, like that. Please, Jordan.
Is there an F triple prime?
It actually can theoretically go on forever. So there is, and it can actually theoretically go both directions forever. Because, every look, this is key, 2 for Julie. Okay, we're starting here by talking about f prime, f double prime. But the names don't mean anything. They're just how one graph compares to another. So we could have started by putting an f double prime in this column, an f triple prime in this column, etc. And the rules would be identical, because it's not an absolute thing, it's a relative thing. It's how one graph compares to another, not how f strictly compares to f prime. So it really can grow in both directions forever, theoretically. Please, Joey.
Would there be like a pattern? Like after a while, would you start seeing like recurring graph shapes?
For certain examples, yes, but not in general. So in general, it's this little kind of, I've got to start over here, it's getting way too cluttered. Clear this off. This little part here repeats right here. You should see it like a little staircase. And then this part here repeats as well. So that just keeps repeating. And it would be like a staircase in both directions. That pattern is absolutely repetitive no matter what function we look at. Does it ever kind of circle back in a way like you were saying? It can, but not in general. So it's not something we memorize. So. Well, please, Mason.
So is the answer B on this question f double prime?
Answer B.
Yeah.
That's well done. Let's make sure you got that right. So here's what Mason did. 2 more for Mason. He said, wait a minute. So if I look at answer C, that was our f prime. We've already checked that out. If you now just do the same thing, and we can use Danica's chart as a shortcut, we could say, okay, here's a couple of things I can look at. If f prime, this f prime is always concave up. This f prime is always concave up. If a graph is always concave up, that means the slope of that graph is steadily increasing. And you can see it right here. The slope of f is negative. Now the slope of f is less negative. Then the slope of f is even less negative. Then the slope of f is 0. Slope of f switches to positive. And then the slope of f switches to more positive. So the slopes of this f prime graph are definitely increasing. Well, if you look at B, if B were f double prime, the y values of f double prime are increasing steadily. That is a perfect match. If f prime is always concave up, then the y values of f double prime have to always be steadily increasing. That's dead perfect. Please, Mike.
So in the f of x, like if you look at where the tangent lines are 0, those are going to be the zeros of the f prime. Is there any way to like see that pattern using like just the equation? Like, is there an easy way to represent where the tangent line is 0 by just looking at an equation?
I would say not necessarily easy.
So you might just want to graph, like literally graph it out, look at where the zeros are, and then that would tell you where the zeros are of the f prime.
You certainly can do that. For our class, two more for Michael, if you're looking at me. Okay, for the purpose of our class, they're never going to require you to do what you just, well, kind of. I'm trying to think for how we, okay, for now we're just doing it purely graphical. So for the Unit 1 test, all you're expected to do is what we've talked about. Look at a graph of f, be able to identify the corresponding graph of f prime. So you can do exactly what Michael did. You can say, hey, f has a slope of 0 here and a slope of 0 here. That means the y-coordinates on f prime have to be 0 in the right spots. That would have led me to think this was possibly correct, and this one. And it would have led me to cross off these two. They do not have values of 0, y values of 0 in the right places to correspond properly. So that would work, and then I can kind of go from there. You won't be asked to go further than that for a bit. Like when we get to Unit 3, we'll start doing a little bit about what you're talking about. So we will go find the zeros of f. We'll start with f. We'll learn how to calculate the formula for f prime. And then once we have the formula for f prime, we can look for the zeros of f prime. But we won't do it directly from f. We'll take the derivative first.
Why would understanding the zeros of f prime be useful?
Oh, that's right. I got that backwards. My bad. Oh, no, that's right. Because the zeros of f prime are where the slope of f is going to be 0. So if I know where f prime has a 0, that's what this is. That tells me exactly where f would have had a slope of 0. And that will prove useful.
Okay.
Two more. Please, Kaylee, you had a question.
But yes, will we ever be asked to find x double prime, or are we just going to be asked to find x prime?
Gotcha. Most of your work will be comparing like this column to this column, or this one to this one. It's not very common that you look at all three simultaneously, but it does happen. And we'll practice that. It's really not, I would not call it more difficult at all. It's just the same kind of sequence of thinking. And Danica's chart really helps me sort it out. So we will do some of that, but it's not hard. So two more. Please, Tom.
Correct me if I'm wrong, but would f triple prime just be a line that the slope is 0 and the y value is at 1?
Two for Tom. You are in no need of correction. That is well said. Here's f. This was the correct f prime. Mason correctly identified this would have been the correct f double prime. And so then we just do it again. We say, hey, this f double prime graph, one way to look at it is you could do this. You could say the values of f double prime are always increasing. Therefore, the rate at which f double prime is changing must be positive. Therefore, f triple prime, so you don't have to even do that. You just come over here and say, oh, I'm going to call that f double prime, which means this now changes to f triple prime. And if f double prime's y values are steadily increasing, then every value on f triple prime must be a positive number. But Tom also noticed, I believe, that the slope here of this f double prime doesn't ever change. The slope is just always the same positive value. So when we go plot those slopes as f triple prime, running out of room, so if I drew an f triple prime graph, I would have nothing more than a bunch of dots where every y coordinate is just a positive number. So every y coordinate here is a positive number. And so this is what you're saying, right, Tom?
Yeah.
That f triple prime would look like that. It's perfect. Just check the room. Who knows what f quadruple prime would look like? Hands up. What would the graph of f quadruple prime look like? You're just translating slopes into y coordinates. That's all you're doing. So what would the graph of f triple prime look like? All hands. Not bad. Pretty good. Let's go, Eliza.
Is it going to be a flat line across 0?
Perfect. Because the slope of f triple prime is always a value of 0, constantly. So if f triple prime is always a value of 0, then when I draw the dots for f quadruple prime, I get something like this. If you knew that, give yourself 2 more. It's perfect. Was that your comment? Did I get yours right, Tom?
Yeah.
Just making sure. Yeah. Oh yeah, please, Cameron.
Does that pattern repeat then for every subsequent prime then? Because they're all going to have a slope of 0?
So that kind of goes back to Joey's question about, like, are there patterns that we're going to observe? If we're dealing with what's known as a polynomial, polynomials are power functions that are being added together, like x to the 4th plus x cubed plus x squared, etc. This one here turns out to be a 3rd degree polynomial. Therefore, f prime is a 2nd degree polynomial. F double prime is a 1st degree polynomial. F triple prime is a 0 degree polynomial, it's just a constant. And therefore, f quadruple prime is simply always 0. F to the 5th prime, quintuple, I guess it's quintuple, I don't know. That would also be the same thing. So from this moment on, every subsequent f, to the 5th prime, to the 6th prime, to the 7th prime forever is just this. And that's true of polynomials. They will always eventually become just a flat line. But it's not true of every function we study, just polynomials. Please.
Is how many times the rate? I mean, how many times? What would you call it when the slope goes from positive to negative? Is it
When the slope changes from positive to negative on f, we call that a relative max of f. The slope changed from positive to negative.
Yeah, so is like the number of times that happens a good indicator of how many like f primes you can take, or I guess derivatives you can take?
Only for polynomials.
Only for polynomials.
And still not something to memorize because it can fool you. Like a 3rd order polynomial can look like this. Here's a better one. This right here is a crude graph of like an 8th order polynomial.
An even number, yeah.
Yeah, so you wouldn't want to memorize that, but I do know the pattern you're seeing.
Yeah.
And it's kind of one of those, hey, that sometimes works, but not always. So yeah. Please, Eliza.
So in the past packets, we have been looking at like jump discontinuities and like numerical discontinuities. How would we see those translate onto like f prime graphs?
Gotcha. I gotta have all eyes. 2 more for Eliza. When you see that, so the reason they had us study limits was to get you to be comfortable with what we did with Desmos, where we said, hey, we can do a secant slope to the left and a secant slope to the right, and we can fix this. It's like we spread out the dots, something like that, to do the 2 different secant slopes. And then we can take the limit as h goes to 0. That's why we studied limits, to get kind of that comfortable. The reason they had us study discontinuities, jump, removable discontinuity, vertical asymptote discontinuity, is so that when we try to do this process with the 2 secant slopes, we'll discover that at a discontinuity, this is not possible. Like what will happen is the 2 secant slopes will not get closer and closer to the same value like they are here. They just won't get closer and closer to the same value. They'll remain separate and distinct values at any discontinuity. We'll study that a little bit more later, but so at a discontinuity, the slope is undefined, which they will test you on when you look at a graph like this. If this f had a discontinuity, the appropriate f prime would have to have an undefined point where the discontinuity occurred. That makes sense. 2 more. Okay, cool. Let's stop this particular video. That was an outstanding discussion of problem 31.